Okay, hello everyone. So I'm just going to make a few quick videos to sort of draw together the stuff we've been talking about with partitions over the last few weeks. So the story so far is that we are using Pn to denote the number of partitions of n. So if you want to look at the partitions of 6, there are 11 of them. I've listed them here. 6, then 5 and 1, so we should read that, and then 4 and 2, and so on. So I'm listing them with increasing numbers of parts, and then for the ones with the same number of parts, we're doing big parts first where we can. So there's one partition of 1, there are 2 partitions of 2, 3 partitions of 3, 4 partitions of 5, and 7 different partitions of 6. That's of 5, which is what that is there. We then defined a generating function for these things. We actually started with a 1, and then we had one partition of x to the of 1 giving us the 1x to the 1, 2 partitions of 2 giving us 2x squared, and so on like that. We then discovered that we could express that generating function as this rather daunting infinite product of infinite sums. And the reason for this is essentially if I want to look at the coefficient of x to the 4 in this massive product, there are various ways I can get an x to the 4. I don't need to take any consideration of the brackets here on the right, because I have to choose 1 from each of those brackets, because all of them have higher powers of x in them than 4. I only need to focus on the brackets on screen. How can I get 4? Well, I could choose an x to the 4 and a 1 from the other 3 brackets, or I could choose an x to the 3 here and an x to the 1 from here, or I could choose an x to the 2 from here and an x to the 2 from here, but expressing that as an x to the 1 plus 1. Or I guess I could choose all the x to the 1 plus 1 plus 1. So what we see is that the number of ways of getting x to the 4th in this product is precisely the number of partitions of 4. We then also observed that each of these brackets is a geometric progression with first term 1 and common ratio x to some power, depending which bracket we're in. And so we used the formula for the sum to infinity of a geometric progression. Here in the background we have an assumption that the magnitude of x is less than 1, and therefore that all of these geometric series do converge. As I mentioned, there are some technical details which we are skating over and which will await you in the beginning of an undergraduate maths course. But for now, this is fine. Alright, we then looked at the denominator of this generating function, which looks a lot like the generating function for partitions of n into distinct parts, but it's not the same because there's a minus sign in each bracket. And we started doing some multiplying out, and we discovered, amazingly, and this is amazing, that most of the coefficients were 1 or minus 1. Or rather, most of the coefficients were 0, and the others were all 1 or minus 1. So why is that true? Okay, so we have to study the coefficient of x to the n in this product. And to find that coefficient, we need to look at the number of ways of partitioning n into distinct bits. So we'll take n equals 8, as an example. Right. So I've written out there all the partitions of 8 into distinct parts, and I've separated them out into even numbers of parts on the left and odd numbers of parts on the right. And basically, what you need to do is you need to realise that the coefficient of x to the 8 in this product underneath, well, there's a minus x to the 8 from taking this bracket here, and that corresponds to this partition of 8. Then there's a plus x to the 8 from taking this minus x to the 7 and pairing it up with this minus x, and obviously all the way through taking 1s from every other bracket. So that contributes plus x to the 8. The 6 and the 2 contribute plus 1 as well, 1 plus 1x to the 8, as do the 5 and the 3 from this partition. Finally, we have these two partitions into 3 parts, and because each of those has an odd number of parts, they contribute minus x to the 8. Conclusion, we get 3 terms of minus x to the 8 and 3 terms of plus x to the 8, so the coefficient of x to the 8 is 0. Okay, so our next job is to try and understand why so many of the coefficients in this infinite product E of x are 0, and also to see whether there's any way to understand the ones that are not 0. We saw before that a partition is 0, the coefficient of x to the n is 0 if the number of ways of partitioning n into an odd number of distinct parts equals the number of ways of partitioning n into an even number of distinct parts. So to show that that very often happens, we want to find a natural way of pairing up partitions of n into an odd number of distinct parts with partitions of n into an even number of distinct parts. We also expect that that pairing will work most of the time, but for some particular values of n, we might be left with one partition which is awkward, which doesn't have a partner. And if that partition is into an even number of parts, we expect a coefficient of +1, and if it's into an odd number of parts, we expect a coefficient of -1 in this product. So we talked about this in the session, and the idea we came up with was to look at the Ferrers diagram, or the dot diagram for a particular partition, and to sort of perform the following manoeuvre. If you look at the shortest or the smallest part, which I've called S in blue, and if that is sufficiently small, then you remove those dots from the diagram, removing the bottom part, and add S dots to the first S rows, or one dot each to the first S rows of the diagram. So you're kind of taking that smallest part and you're kind of moving it up there. You're going across the diagram. So these blue ring of 4 dots is actually becoming these 4 dots down here. That works if S is small compared to D, the length of that diagonal. Okay. If, on the other hand, S is big compared to D, then you try and do the reverse process. So you take D, strip off a dot from each of the first D parts of the partition, and add a new part of size D at the bottom. That'll be fine, provided D is small enough compared to S that we don't break the parts are distinct rule. Okay. Another really important thing about this procedure we discovered is that we hope that if you take a particular partition and apply the rule, which is look at S and D, if S is small, move it up, and then apply the rule again, look at the new S and the new D, if S is big compared to D, move the D down. So if you do that, you hope to always get back to where you started. That's really, really important, because that shows that the rule that we're developing forms a pairing between partitions and not sort of a weird chain of partitions. It's really important that they're partnered one with another and not X with Y with Z or anything strange like that. Also worth mentioning, the rule we're kind of articulating definitely always pairs an odd partition with an even partition because it changes the number of parts by 1, no matter which way you do it. Okay, so let's see it in operation again. Here's a partition of 9 into a 5 and a 4. You look at S, which is 4, you look at D, which is 2. D is small compared to S, so our suggestion is strip off those top 2 dots and stick it at the bottom, creating a new part of size 2, and that works just fine. You move across over here. If you look at this partition, you look at D, you look at S, S is 2, D is 3, S is now the small one, kind of because D was the small one last time. And that means that our rule suggests strip off S, the smallest part, and add a dot to the first S parts, which neatly takes you back to where you started. And then we encounter our first awkward partitions. Partition of 5 into 2 parts, 3 and 2. Turns out neither move works here. If you try and strip off the S and add a dot to the first S rows, you'll go to a partition of 5 as 4 and 1, 4 plus 1, and that's no good, partly because that partition already has a partner. It's partnered with just 5, but also because we haven't changed the parity of the number of parts. So we haven't attempted to pair a partition into 2 parts with a partition into either 3 parts or 1 part. Okay, so that's awkward. You can't do the other move either. You can't strip the D off and add it at the bottom, because that would lead you to the partition 2 plus 1 plus 2, and that's not a partition into distinct parts. So it's not in our sort of space of discussion. So that's an awkward partition. That's good. We expected an awkward partition because we had a coefficient of +1 in the x to the 5 place in our expansion. It's plus because that's a partition into 2 parts. We have another awkward partition at 7, and for the same sort of reasons, you can't strip off the S because it just won't work. You'll get, in fact, 5, 1, 1 or something which isn't distinct, and you can't strip off the diagonal either because you'll break the distinctness rule. Okay, so in summary, here's our rule. If S is less than or equal to D, you try and strip off the smallest part and sort of decorate the top S rows of the diagram with an extra dot. On the other hand, if S is more than D, you try and move that diagonal down. So you try and take one dot off that each row in those first D rows and create a new part of size D at the bottom. This mostly works and mostly is its own inverse. The posh word for that, by the way, is an involution. There are some difficulties if the diagonal intersects the shortest part. That's when things can start going wrong. So if you look at our two awkward partitions, they have this peculiar property that the diagonal intersects the shortest part. And that happens precisely if the length of the long diagonal is equal to p, the number of parts in the partition. You can see that up here as well. Here the diagonal intersects the smallest part, but it didn't cause a problem because S was not just a bit bigger than D, but much bigger than D. And somehow that made it okay. Again, here we have S intersecting with D, the shortest part intersecting the diagonal, because D is 3 and P is 3. But again, here it somehow didn't seem to be a problem. And here again, we have the diagonal is size 4, and there are only 4 parts in the partition. But again, it's somehow not a problem. Here, they're not intersecting. So, summary, if S is small, try and move it up. If S is big, try and move down the diagonal. Now we need to look at the detail of this, and we need to check. Basically, what we need to check is that we can mostly find everything a partner, and crucially, that you take a partition, you find its partner using this method, and then you look at that result. If you then try and find the partner of that resulting partition, you must get back to where you started. All right. This table probably has more detail in it than strictly is required. It's a little bit non-minimal, but I wanted to make sure that it was really clear we hadn't missed any partitions in our discussion. So, 2 cases, first of all. Is the number of parts the same as the diagonal? That is to say, does that green diagonal D reach all the way down to the bottom of the diagram? Or is the number of parts more than the length of the diagonal? That splits our space into these two columns. And then we sort of expect there to be no trouble if S is much smaller than the diagonal, and I've said that to be less than D minus 1. And we also don't expect any trouble if S is much bigger than the diagonal. I've said S bigger than D plus 1 at the bottom. And then we think maybe there might be some trouble if S is nearly the same size or the same size as D. And I've perhaps slightly overkill, but I've checked 3 different cases: S is D minus 1, S is D, and S is D plus 1. So certainly that covers every partition. Every partition you could possibly hope to meet. If I tell you S the smallest part, D the length of the diagonal, and P the number of parts, then you can say which of the 10 regions in this table it belongs to. Okay, let's see how we read this. So you start with a partition SDP, shortest part, diagonal, number of parts, where here we're saying that the number of parts is more than the diagonal, and that the smallest part is less than D minus 1. Because the smallest part is so small, our aim is to move it up using that arrow. So the new partition, the smallest part, still in the first coordinate, still in blue, is now S dashed, where S dashed is some number bigger than S. We also have that the new diagonal is precisely composed of the S dots we removed from the smallest part before. And finally, we have that the number of parts has gone down by 1. Now, why is this important? Well, we now need to check what happens if we focus our attention on this partition. Well, let's check. The shortest part here, S dashed now, is definitely more than the diagonal, because the diagonal is the old S. So we're in the bottom 2 rows somewhere. And then we just want to check quickly, are we in a situation where the number of parts equals the diagonal? And I think the answer is no. Okay, so the number of parts is gone down to P minus 1, but it's still greater than or equal to D, because P was more than D. And S, the length of the diagonal, is definitely less than D minus 1. So we're not in a situation where the number of parts equals the diagonal, so we're somewhere on this side. And all we need to check is that no matter where we are on this side of the table, the corresponding move is bring that diagonal back down, the exact opposite of the move we made earlier. So in that case, everything's partnered with itself. Okay. So let's look at a sort of slightly more awkward one on this side. We're not going to do all of them, but let's look at this case here. We've got a partition S, D, and P, where we now say that S is just one less than the diagonal, and that the diagonal goes all the way to the bottom row. So what happens here is we're told that because S is less than D, our aim is to move that shortest part up. What happens when we do that? Something a bit strange happens. Okay, the number of parts goes down by 1. P goes down to P minus 1. The new diagonal is exactly the S parts from the shortest part. That's fine. But something slightly strange happens, which is that the new shortest part is actually 2 more than it was before. And the reason is that I draw a quick diagram with this situation. Okay, so there's an example of this. We actually saw it earlier, but the diagonal there is 3. It's equal to the number of parts, and S, the shortest part, is 1 less than that. And when you move it up, what happens is that you get an extra dot here and an extra dot there, and so you can see the shortest part has got 2 longer. And that always happens. Okay. So now let's focus our attention on this partition and see whether our instructions are to do the opposite, to bring the diagonal down, if we encounter a partition like this. Well, in this partition, S, the shortest part, is more than D plus 1, because it's D plus 2, because D, the length of the diagonal in this partition, is equal to old S. But if S is more than D plus 1, then it doesn't matter where we are in the table, our instructions are going to be move that diagonal back down. Okay? So I'll leave it to you to go through and check the others, but in every case in this table, you take a partition, you perform the operation, and then you perform the same process on the result, you'll get back to where you started. And the only ones where we have difficulty are exactly the ones we anticipated having difficulty with earlier, which are when P equals D and when S is either equal to P or 1 more than P. In particular, we have difficulties when S is D is P and when S minus 1 is D is P. Here are the diagrams for those. So P is 1, 2, and 3. And we can see that for each of these cases, it's quite easy to develop a formula. The case n equals 4 is illustrated there. If S is D is P, you have a 4 by 4 square and then the third triangle number. And if S is D is, if S minus 1 is D is P, then you still have the 4 by 4 square, but then the fourth triangle number on the right. So there are the formulae, and there are the sequences that we get. As promised, we're now going to draw things together, and we're going to see how we can use what we've learned to compute the number of partitions of 100. That would be very, very difficult to do by hand, but we'll discover that we can do it reasonably efficiently. We've already seen that the generating function for the partition numbers is 1 over this infinite product E of x, and we've got a good understanding of the polynomial, the series E of x. Almost all the coefficients are 0, sometimes they're 1, sometimes they're minus 1, and the non-zero coefficients occur precisely if n, the power, has an awkward partition. That's a partition where the dot diagram can be drawn essentially as a pentagon, a sort of square plus a triangle. So either n squared plus the n minus 1th triangle or n squared plus the nth triangle number. And that comes as a plus or a minus 1 depending on whether n is an odd or an even number. Okay, so taking this line of algebra up here and multiplying it up, we discover that E of x, this infinite product multiplied by the generating function for the partitions, that's 1 plus number of partitions of 1 times x, number of partitions of 2 times x squared, number of partitions of 3 times x cubed, and so on. That product is just equal to 1, so if you pick out the coefficient of x to the n for any n bigger than 0, n bigger than 1, in fact, bigger than 0, that coefficient will turn out to be 0. Okay, so let's, for example, think about the coefficient of x to the 10. How could you get x to the 10s from this product? Well, you could take from sort of somewhere way down here, you could take p10x to the 10 and combine it with 1, Or you could take p9x to the 9 and combine it with this minus x to give minus p9x to the 10s. Or you could take p8 somewhere down here and combine it with this minus x squared. And then you don't need to worry about p7 or p6 because the next non-zero term in e of x is 5, and you could sort of pair that up, I suppose. You could take p5x to the 5 and combine it with this plus x to the 5. And that would give you plus p5x to the 10. And the only other one you'd need to worry about would be this x to the 7 with p3x to the 3. All of those together give 0, as we've seen here. So rearranging to make p of 10 the subject, we see that p of 10 is p of 9 plus p of 8 minus p of 5 minus p of 3. This is a little recurrence relation that allows us to generate the next partition number from the preceding ones. More generally, we've got that Pn is equal to Pn minus 1 plus Pn minus 2 minus Pn minus 5 minus Pn minus 7 plus Pn plus 12 minus 12 plus Pn minus 15 and so on. The numbers here are precisely those pentagonal type numbers. And whether you're adding or subtracting them depends on the parity of the number of rows in those awkward partitions. So we can use this to actually start computing some things. We'll need some conventions. We'll need the convention that we start with there being one partition of 0, and that if this formula asks you to work out the number of partitions of a negative number, you just ignore it. There aren't any partitions of a negative number. Okay, off we go. We said that P0 was 1 by convention. P1, therefore, is the same as P0. All the other terms disappear. That's 1. P2 is P1 plus P0. That's just 1 plus 1, which is 2. P3 is the previous two added together. P4 is the previous two added together. It looks a little bit like it's going to be like the Fibonacci numbers, but then it breaks as you get to P5, because P5 is P4 plus P3 minus P0. So you get 7 partitions of 5, 11 partitions of 6. We had to add another term to our recurrence for doing 7. So P6 plus P5 minus P2 plus P0 turns out to be 15. The next one's 22. The next one after that's 30. The next one after that's 42. All those 4, we were able to compute with only 4 terms in our recurrence, and that's basically we're winning a lot of efficiency because of the number of zeros in the expansion e of x. Okay. In general, the non-zero terms are sort of, well, they come in sequences that are basically n squared plus half n squared. So, if you wanted to get 20 non-zero terms, you'd be looking at 10 squared plus the 10th triangle number, 10 squared plus the 9th triangle number. Those would be the sort of 19th and 20th non-zero terms in the expansion e of x. So you're looking at about 150. So with just sort of 20 terms in the recurrence, which is actually still doable by hand, but certainly quick with a computer, you could start working out the number of partitions of numbers up to 150 quite easily. Okay, so I said by hand this would be totally plausible, but with a computer it's very, very easy indeed. Just looking over here on this side to start with. Correct my program. So if you've never seen a Python program before, hopefully it won't matter very much. Line 2, n is 200. We're going to go for the first 100 partition numbers. We're going to start with a list in square brackets of the pentagonal numbers, these numbers with the awkward partitions. They started with 1 and 2, and then we're going to add new ones. To do that, we're going to need to know what a triangle number is. So I've defined a little function that returns the nth triangle number. Hopefully it's a formula you've seen before. Notice we're using a star for multiplication. This int here is just forcing the result to be a whole number. So Python likes different types of thing. Okay, we had 2 different kinds of pentagonal numbers. We had n squared plus the n minus 1th triangle number and n squared plus the nth triangle number. I've called those pent A and pent B of n. Notice 2 stars for exponentiation, for to the power of. Right, now we're going to generate a list of those awkward numbers. Okay, there's a little counting variable called little n is 2. Pentagonal minus 1 refers to the last entry in this list here, and this list is about to grow. So this says, look at the last entry. So far it's 2. Is that less than n plus 1, 101? Sure it is. Let's execute what's happening in this indented block. We're going to append, stick on the end of the list of pentagonal numbers, pent A of n, pent A of 2. We look at what pent A is. That's 2 squared plus the first triangle number. That's 5. So we're going to decorate this list with a 5. Then we're going to decorate it with pent B of 2, which is 2 squared plus the second triangle number, which is 7. Then we're going to swap n for n plus 1, so n's going to go up to 3. We're going to look at the penultimate entry in the list. Is it still less than 101? Sure it is. Run through it again. So then we'll add on 3 squared plus 3, which is 12, and 3 squared plus 6, which is 15. Send n up to 4, and do it again. Okay, that will fill up the list of pentagonal numbers to all the pentagonal numbers until we get some that are bigger than 101. Next, we're going to actually generate the partitions. So we start with partitions of 0, there's one of those, partitions of 1, there's one of those. And then we say, while the length of this list is less than 101, so until the length is 100, what are we going to do? We're going to start with a temporary number, that's going to be our next partition, and we're going to stick that on at the end. How are we going to build this temporary number? Well, basically, we're going to kind of add or subtract entries, earlier entries in the list of partitions. So, but we're only going to do that going from stepping back by a pentagonal number. Okay, so we're going to go through the list of pentagonal numbers. If I is less than the length of the partitions we've already calculated, so if we've only calculated 10 partitions, we're only going to use pentagonal numbers less than 10, less than or equal to 10. We're going to take our temporary number and we're going to add or subtract the minus ith entry. That's I from the back of the list of partitions. And we have to get this going as plus, plus, minus, minus, plus, plus. And to do that, we're doing minus 1 to the power of half of this counting variable power. Okay? Don't worry too much about the details. I guess the key thing is it's a short program. Finally, at the end here, we're going to print them out 5 at a time. I'm going to hit run up here, and our entries will appear over here. And look at that. Just like that, we've got the number of partitions of the first 100 numbers. The number of partitions of 100 appears to be approximately 169 million, so I'm jolly glad we didn't write them by hand. And we're sort of done. We've done what we set out to do. Congratulations to us. Final thing I'd just like to notice is I've printed them in blocks of 5 at a time, and this was done by the Indian mathematician Srinivas Ramanujan, and he noticed that if you print them out 5 at a time, the last entry in each row, somewhat mysteriously, always appears to be divisible by 5. And that turns out to be true. This is the first of the so-called Ramanujan congruences, and there are a couple of others. And proving those is, well, proving that one in particular is quite interesting. Not super easy to find stuff on it, but you can find some stuff online on it, and it's not so hard that you couldn't engage with it, but it does sort of turn the next corner in this story. So that's something to think about over the long summer.